Hello everyone, I'm Ruotong Yu. It's a great honor to present our work, Building Embedded Systems like it's 1996. This work has been done in collaboration between the University of Utah, Stevens Institute of Technology, University of Purdue, Norwegian University of Science and Technology, Delft University, and Cyber ITL Independent Research Group. Embedded devices are running everywhere to connect the physical world with the digital world. By estimation, there are more than 35 billion embedded devices installed in the world. This large-scale deployment makes the security of embedded devices critical. As we know, many mitigations are used to protect the desktop system from different kinds of attacks. These mitigations include both user space and kernel level. The most famous ones include stack canary, non-executable stack, address space layout randomization, and so on. The mitigation used by desktop binaries can also be applied to embedded systems. However, preliminary results from our collaborators indicate that mitigation is rarely applied on embedded devices. The table represents the result from our collaborators by evaluating the mitigation in popular routers. Looking at this table, binaries from Ubuntu desktop are well protected with stack canary, non-executable stack, and relocation read only. In comparison, all the mitigations are almost missing in the popular routers. This motivates us to extend the study into a much larger scale. In this paper, we focus on three research questions. First, do embedded devices adopt attack mitigations? And second, is the adoption of attack mitigations improving over time? And third, if the attack mitigations are missing, what are the possible reasons? To answer all three questions, we perform a large-scale study on evaluating the mitigation adoption on embedded devices. Our study focused on Linux-based devices with both user space and kernel-level mitigations. We focus on Linux-based devices because they are not only represent the dominant type of embedded devices, but also support most of the mitigations. Before we answer the questions, let's first see the challenges on performing such a large-scale analysis. The first is to build a high-quantity dataset. The previous dataset are outdated and some are even invalid today. The second challenge is to unpack the firmware images. Firmware images are organized in diverse formats, and some information cannot be fully recovered. And finally, we need a solution to accurately identifying attack mitigations. There are existing tools, but they all have design limitations. Our design is straightforward, which has four major components. The first stage is to use web crawler to collect firmware images from vendor website. We only focus on the publicly available firmware images for ethical consideration. Once the firmware images has been collected, the next step is to unpack the firmware images. During the unpacking process, we collect both Linux kernel and file system. We will then perform the mitigation identification. The last step is to analyze the result. So in total, we collected over 18,000 firmware images from 38 vendors. The firmware images range from 1998 to 2021 and contains the most common type of embedded devices. To unpack the firmware images, we use a firmware unpacking tool from previous work, firmware. The tool is designed on top of Beamwork and capable of extracting file system and kernel within the firmware images. We call a firmware is successfully unpacked if at least a file system or Linux kernel is extracted. The table presents the number of images we collected and unpacked for each vendor. In amount of 18,000 firmware images, we collected 10,000 and the success rate is about 59%. This includes over 9,000 file systems with 3 million ELF binaries and 8,000 Linux kernels. So in terms of user space mitigation, we include all the mitigations that are both integrated into standard compiling toolchain of Linux system. The collection includes stack canary, 45 source, position independent code, relocation rate only, and non-executable stack. We follow a similar rule on selecting kernel-level mitigation. First, the mitigation is active in Linux distribution. Second, it has been released over 3 years, so the vendors have enough time to deploy them. And finally, it's applicable to deployed systems. So far, we have discussed the steps of our study. Now I would like to share the interesting findings to answer the proposed questions. The table on the right presents the number of ELF binary and the adoption rate of each mitigation for every vendors. The binaries from Debian packages in stable distribution for desktop is used as baseline. Comparing the result, we can see the adoption rate of mitigation by embedded binaries are very low on average, significantly falling behind the desktop binaries. For example, over 85% binaries from desktop environments are protected with stack canary, but the number drops to 29% on embedded devices. On the other hand, the adoption rate of mitigation dramatically vary across the vendors. Some good performance vendors can achieve 80% adoption rate on stack canary, while the bad one completely fails to adopt it. We have more interesting findings by breaking down the binaries with architectures. The figure presents the adoption rate of user space mitigations by binary from different architectures. The ARM binaries compose the largest group. They have a moderate level of adoption rate for all the mitigations. MIPS as the second largest group has the lowest adoption rate in nearly every mitigation. You may notice the adoption rate of non-executable stack in MIPS is much lower than the others. This is caused by the hardware restriction of MIPS. In general, x86 and ARM64 binaries have relatively higher adoption rate because these binaries are running on newer building environments. The adoption in kernel-level mitigation is also disappointing. According to the table, in amount of over 3,000 analyzed Linux kernel, only 159 of them are protected with stack protector. The other protections are almost missing. The evidence indicates that kernel-level mitigation are rarely adopted. So to answer the second question, we keep track of the mitigation adoption change over time. This figure presents the user space mitigation change from 2010 to 2021. We can see only adoption of non-executable stack present a constant positive trend. The others are not improving and even get worse. Here is another figure indicates the change of individual firmware. Each point in the figure represents a firmware with multiple versions. We compared the adoption rate between the oldest version and the newest version. According to the figure, most of the firmware present no change at all. Some of them are even getting worse. We also keep track of the kernel-level mitigation change over time. This figure presents the result for stack protector, as this is the only mitigation commonly identified in the kernels. The overall adoption rate is low, but it's good to see the adoption rate consistently increased over the past decade. This is because the vendors are using newer version of Linux kernel, and this brings more positive changes. Remember, the third question to answer is to figure out the possible reasons of missing mitigation. The first potential explanation comes from the restriction of building tools. The table presents the availability of mitigation in different versions of buildroot, which is an automatic building tool used by many vendors. We can see many of the mitigation is not available before 2012. More mitigations are enabled after 2017. If the vendor didn't update the building tools in time, they would not be able to apply those mitigations to their products. Another reason is the large number of binary reuse. The left table indicates the number and ratio of unique binaries in each of the vendors. Obviously, vendors largely reuse binaries. The binary reuse also happens between vendors. The heat map on the right presents the binary overlap across the vendors. The darker color represents a larger number of binaries. If those reused binaries are not well protected, the missing of mitigation will easily spread to many more devices. So another possible reason for the lack of mitigation comes from overhead. The table presents the overhead of storage space, memory usage, and runtime performance when each mitigation adopted. From left to right, the mitigation is enabled one after another. We can see mitigations like stack canary, precision independent code, read-only relocation have observable overhead. However, it's hard for us to determine if the overheads are affordable or not. This needs to be confirmed by the vendors. On the other hand, we're also wondering, are the low adoption rate of mitigations attributed to the lack of vulnerabilities? We hereby perform a case study of embedded vulnerabilities. It shows that memory corruption vulnerabilities are common on embedded devices. For example, we have found two memory-related CVEs reported on 2021, which affected millions of devices rely on Realtek SDK. As a further step, we identified 1,360 binaries packaged as part of above Realtek SDK. These binaries present no broader adoption of attack mitigations. Thank you for your listening. If you have any question, you can investigate our paper or contact us with email.